Good morning, guys. Today we are going to do a section from chapter 8, and with chapter 8 we're going to do what we did with chapter 7. Chapter 7 we did just 3 lessons on logarithms, and so we're going to do a few lessons on rational functions. So that's what the title of this chapter is. It's about rational functions. So let me just show you what one is. A rational function is a function that can be written like this. Now, this looks real complicated, right? But remember, this just means y. So y equals this stuff. This is just function notation of y. Y is a function of x. It depends on what x is. And then these are little mini functions in themselves. So it's a polynomial over a polynomial. It's an equation over an equation. Now I say equation. It's an expression because there's no equal sign in this little thing and no equal sign in this little thing. Anyway, so let me show you one. It looks like this. See, it's a fraction with equations in the fraction. Expressions in the fraction. And it looks like this. See, a fraction with some expressions, like this, like this. So this combines two pretty complicated concepts. Fractions give people trouble, and then these kind of expressions give people trouble because that was where we did all that factoring. So like factoring that thing and factoring this thing. So it combines a couple tough ideas. So we're only doing a few sections, and the reason we skip the first couple of sections in the chapter is because that's all about graphing these. And if I wanted to graph something like this, or better yet, something like that had the expressions in them, I would use a graphing calculator. And in most college classes that you have to take for credit, they'll allow the use of a graphing calculator to do that kind of heavy graphing. All right, so first let's talk about something interesting that happens with these. And something that happens is we get this thing called points of discontinuity. We get some points of discontinuity. And so that's a place essentially where there's like a break in the graph. And so let me just show you some pictures, and I want you guys to sketch these with me. There are two types of points of discontinuity, or places where the graph will kind of have a break in it. The first type are called asymptotes. So ASYMPT, asymptotes. Asymptotes. Okay, so that is likely a brand new word for you, so I wouldn't blame you if you wanted to, like, I don't know, say it 3 times. Asymptotes, asymptotes, asymptotes. And see, this is kind of good about distance learning. You can do that in the privacy of your own home and nobody even knows. So hole in the graph, that's the other kind. If there's a hole in the graph. So there's 2 types of what's called points of discontinuity: asymptotes and holes in the graph. Okay, so I'm going to draw some pictures of some asymptotes. So if you had a curve, a graph coming up, and it goes towards this line right here, but never reaches the line, it just keeps going towards it and towards it and towards it like this. That right there is called an asymptote. See, this graph is not going to cross that line. It's going to keep approaching that line and getting closer and closer and closer and never reach it, which is a little bit hard to understand, but that's what's happening. And if you want to think about approaching something and never reaching it, just imagine that you're standing in class or in your room or wherever, and there's a door right here. And let's see, each hour you move halfway to the door. So you move there, and then 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 you move there. If you're always moving halfway towards the door, then theoretically you never reach the door. You're never standing right at the door because each time you're just going halfway and it never reaches it. Or in other words, if you're looking at a number line between 0 and 1 and you keep halving the distance, you're never going to get to 0. So that was ugly. So like if you're halfway there, then you're at a half, and then if you're halfway there, you're at a fourth, and then you're halfway there, you're at a eighth, and halfway there, you're at 1/16, and then 1/30 1/32 and 1/64. You keep approaching 0, but you never get there, which is kind of an interesting math happening, okay? So that is, this is called a vertical asymptote. It's approaching it, but it never reaches it. Okay, this one, I'm gonna use a different color. Maybe I should do my asymptotes in a different color. So I'm gonna make the two axes. That was purple. Maybe purple isn't the best choice. Anyway, the two axes, the x-axis and the y-axis, those are going to be my asymptotes. And so here's a curve approaching both the y-axis and the x-axis, but never reaching them. And sometimes on these funky equations, it happens on both sides. And sometimes they're symmetric and sometimes they're not. I'll make mine symmetric. Like if you folded it in half, they would match. Okay, so there's a vertical asymptote and a horizontal asymptote. And then I'm gonna make this one with those same two asymptotes. So the axes are the asymptotes. Ooh, that's a mouthful. That curve is approaching this one and this one, both axes, and then this curve is approaching both of those. So this is another picture. So see, these equations will look funky if you put them in a graphing calculator and graph them. And so I'm just not doing the sections where we graph them by hand. Okay, let's talk about holes in the graph. Okay, so we did some graphs where graphs were curvy, like a parabola, and we looked at some cubics. We only like sketched a cubic. We never like formally graphed one. But so here's a cubic like that, because it's got 1, 2, 3 parts. And then imagine there's a hole right there. That's what a hole in a graph would look like. It's just a smooth graph, except for there's no value at that x value. There's no y value at that x value. So there's a hole in it. And those could be in parabolas, they could be in cubics. You could have more than one hole in the graph. So yeah, that's what that looks like. And then here's a linear one. Now this one, I'm gonna explain how this happens with one like this. Okay, so we learned a long time ago that, you don't have to write this, I'm just talking, that to graph an equation like this, y equals, let's say y equals 4. So think back to Hoy-Vux, right? So this is a Hoy problem because it's y equals 4, which means this is a horizontal line at 4. So I'm going to graph 1, 2, 3, 4. And so that's y equals 4, but it's the whole line because it's a Hoy-Vux problem. So the whole line, horizontal line, y equals 4. Okay, well, what if I had a function? Remember, that's just y equals. And suppose I had 4 times x plus 1 over x plus 1, like this. Okay? Well, now this would be after factoring. Usually, it may be factored for you, but most of the time you gotta factor it. Well, won't these cancel, right? X plus 1 over x plus 1 cancels. And you have f of x equals 4, or y equals 4. So it's that same graph. But we learned a little while ago that the bottom of a fraction cannot be 0. So we have to think about that value. X cannot be -1, because if it is, that function's undefined. So in other words, for this right here, that graph is not defined at x equals -1. So at -1, there is no value. Which means I have this perfectly normal looking line at y equals 4, but at -1, there isn't a value there. There couldn't be, because it makes this undefined. It's undefined at -1. So that's how you get holes in graphs from, rational functions like this. Okay, so there are 2 types of points of discontinuity, hole in the graph and asymptotes. There's actually more to asymptotes. We're gonna do vertical ones today, horizontal ones next lesson, And then there's these things called slant asymptotes. We are not going to be doing slant asymptotes at all. But here's basically what a slant asymptote is. If you had a line that's going across the graph like this, that a line, or that your graph never touches, it approaches it but never touches it, that would be a slant asymptote. And we are not going to do those. So you don't even have to worry about that guy. I just wanted you to know what it was. Okay, so here's the math, y'all. Well, that's math, but here's what you do. How to find the holes and vertical asymptotes. You take that equation, that rational function, and you set the denominator, which is the bottom, equal to 0. Now, the reason you do that is because you're looking for spots where that function would be undefined. So you set the denominator, the bottom, equal to 0, and then you solve it. And some of them are going to be factored for you, which will be pretty easy, and some of them are not, which are going to be a little more difficult. Okay, so example 1. This one is all factored for you, nice and easy. So you take that denominator, x minus 1, I was solving that thing already, x plus 2 equals 0. Now really what you're saying is it can't equal 0. But to find these places, you set it equal to 0 and then you solve it. So some of you will remember from the factoring chapter that it's just the opposite of these. So x equals 1, because 1 minus 1 would be 0, and x equals negative 2, because negative 2 plus 2 equals 0. If you didn't remember that, to solve these, or if it's a harder one, to solve these, you set each factor equal to 0 and solve them independently. So add 1, you get x equals 1, and subtract 2, and you get x equals negative 2. All right, so here's what we're saying. We're saying that if we graph this thing, there is no, there's an undefined value, y value, at x equals 1. And there's an undefined y value at x equals negative 2. So either there's a hole in the graph happening there, or there is a vertical asymptote. And we'll talk in a minute about how we tell which one it is. Okay, so the points of discontinuity are x equals 1 and x equals negative 2. Now, I can't stress enough that these are not solutions to this equation. These are points of discontinuity. So you may want to write down that these are points of discontinuity. They're pods, okay? X equals 2, x equals 1, and x equals negative 2. All right, next one. See, this one gets a little bit harder because it's not factored for you. And to set that equal to 0, x squared plus 2x plus 1, to solve that by setting it equal to 0, it has to be factored. Now, remember back to the quadratic chapter, there are quadratics that can't be factored. So if you can't factor it, you have to solve it using the quadratic formula if it can't be factored. And by the way, the quadratic formula will always work. So like if you are just like the worst factorer ever, you could plug it into this formula, x equals opposite of b plus or minus square root b squared minus 4ac over 2a. And that'll solve any of them, even if they are factorable. Now, the only downside to that is there's just so much opportunity for error in a formula like that. So I would much rather see some factoring because the process is a little bit easier. Okay, especially when the last number is 1. Okay, so remember this process. You take that last number. If there's a number in the front, you have to multiply that. But there was no number in the front, so you take that last number and you write down all the ways to get a positive 1. So it could be 1 times 1, or it could be negative 1 times negative 1. So this is an easy one. We only have those choices. And we want to choose the product that will add to be this middle number. And the middle number is a positive 2, so it's going to be 1 and 1. So this factors like this, x plus 1 and x plus 1. Here's how you can check it. The outer value is 1x, and the inner value is 1x. That makes 2x. And then we already knew that the last 1 times 1 is going to give you this 1. So we're just checking it with the outer and inner of FOIL. All right, so this is how it factors. That's what this bottom is. So this is 1 over x plus 1 times x plus 1. Same equation. We just changed the form. All right, and so now we find out what equals 0. So this solution would be -1, and this solution would be -1. So there's really only one point of discontinuity. If you forget how to solve like that, you just set each one equal to 0 by themselves and solve. X is -1, x is -1. So you only have to write it one time. So the point of discontinuity is x equals -1. There's something happening on this graph at x equals -1. We'll find out in a few minutes whether it's a hole in the graph or an asymptote. Okay. Same directions, find the point of discontinuity. And this one is a quadratic, the little square right there. So it's also not, it's not factored yet. So x squared minus 1 equals 0. All right, so the way we solve this one is we're going to write down -1, that last number, and we're going to write down the ways to get a -1. Well, if it's -1, it's got to be +1 times -1. That's the only way that breaks down. And when you add those together, +1 plus -1, that's 0. That's why there's no x's in the middle, because there's 0 x's in the middle. That right there is the same as x squared plus no x's minus 1. So the way this factors is x plus 1, x minus 1. And so just showing you why that works, to check this, the outer term is -1x, the inner term is +1x. That's why there's no x's in there, because they canceled. And then to solve it, this solution would be -1 right there. This solution would be +1. Or, in other words, if you set that one equal to 0 and solve it, you get -1. And if you set this one equal to 0 and solve it, you get 1. So the points of discontinuity are x equals -1 and x equals +1. So if you were to graph that, there is either a hole in the graph or an asymptote at x equals -1 and x equals +1. So if we were to graph that, something is happening at those spots. Okay, now we have to talk about how we know which one it is, okay? So to distinguish between holes and vertical asymptotes, to be able to tell which one it is or what's happening there, I want you to consider these two different problems, okay? So from this problem, the bottom is x minus 2, so x minus 2 equals 0, and when you add 2 to solve it, you get x is 2. So we know that there's a point of discontinuity here. So what we've been doing on this whole notes paper is finding out that that's a point of discontinuity. So at this point, what we know is something's happening at x equals 2. Now, if you look back at the original equation, everything's all nice and factored for you. So if it weren't factored for you, we would have to do that. Well, these cancel. So the rule is if that point of discontinuity, if that expression, if that, what's the word I'm thinking of? If that factor cancels with something on the top, that means that there's a hole in the graph. So I'm going to write that down. There is a hole in the graph where x equals 2. And here's why. Because the x minus 2 cancels. That's what gives you holes in the graph. So it's kind of like this one I talked about a few minutes ago, where I graphed that totally normal looking line because that canceled and it gave me just 4. But from the original equation, something was happening and this canceled. So that's why there was a hole right there. And then look at this one. So this one, we have 2 points of discontinuity because x minus 2 times x minus 3 equals 0. Now this is all factored for you. Then we know something's happening at +2 for this one and at +3 for this one. Now remember, those are not solutions. Those are points of discontinuity. And then if you look at the original equation, the x minus 2 does not cancel, and the x minus 3 does not cancel. So what's happening at these 2 points is vertical asymptotes. So there are vertical asymptotes. At this point, the asymptotes we're talking about are vertical. Next lesson, we're going to talk about the horizontal ones. There are vertical asymptotes at x equals 2 and x equals 3. And here's why. Because the x minus 2 and the x minus 3 do not cancel with an expression on the top. Okay, so the last thing I want to do is go back up and look at these ones that we've done and see what kind they are. So on this one, we found out that, that these were our points of discontinuity, but what are they? Okay, so looking at the equation, the bottom we factored to be x plus 1, x minus 1. Now, the top has a negative in front of it, which makes it not match one of these. So what we can do is we can factor out that negative 1 from both of these expressions. And what that's going to leave is an x, so it'll match these guys. There's an x. And then if we factored out to the front a negative 1, then that would leave another negative 1. So think about this. If you distributed the negative 1 back, negative 1 times x would be negative 1x, and negative 1 times negative 1 would give you this positive 1. So it's this same thing just factored. And then you'll notice the x minus 1's cancel. So here's what's happening. There's an asymptote here, a vertical asymptote, and there's a hole there because that one canceled. And then look at this one. This one's all factored for you. Nothing cancels. So this is a vertical asymptote. When they're already factored for you, it makes it a much easier question. And then let's look back at this first one. Nothing canceled. The x plus 1 doesn't cancel, and the x minus 1, doesn't cancel, and the x plus 2 doesn't cancel. So in this case, these are also both vertical asymptotes. Vertical asymptotes. All right, so some of this lesson, some of these problems that you do, they're going to ask you to just find what would be the points of discontinuity. And some of the problems, they're going to ask you what those are, whether they're vertical asymptotes or holes. So just remember, if something cancels, now to determine that, everything has to be factored. So if something cancels, it's a hole, and if it doesn't cancel, then that's a vertical asymptote. All right, so I know these are some brand new concepts for you guys. So hopefully you guys are watching these videos, and because that's how you get this material, this content. And I know it's not the most exciting thing you have to do with your day, but it's real important that we get these last few lessons. We don't have much more. All right, y'all have a great day. Bye.